And then finally we're going to have Adam, who is going to is done a lot of nice work using analytic tools and developing analytic tools in learning. So these are the three courses. If I look at the spectrum of expertise in this room, so there are people in this room who know everything. So there are people in this room who know less than everything. So I encourage all of you to ask questions whenever you want to ask questions, because if you have a question, it's very likely that some other people have questions. It's even more likely that there's somebody who's watching the stream who also has a similar question, so feel free to ask questions. This is a week-long effort, so we want everybody to stay on board. I also want to encourage the speakers to stay within times, because people would need a break and need their breaks between the lectures. Okay, so the first series of lectures given by Adam Klivans from UC Austin, and he's going to talk about, what's your official title?
I don't remember.
I don't know.
No, I'm going to talk about analytic methods in supervised learning. Thanks to Elkanan and the organizers for inviting me. I just wanted to say that as Elkanan mentioned, I'm going to be speaking about a variety of results. I mean, machine learning and learning theory in general is just an enormous field now. And I'm going to be speaking in particular mainly on topics related to supervised learning, which I'll describe in a second. And also results that I think dovetail nicely with some of the analytic tools that Shistov will be talking about, and some of the results that we've seen in previous weeks here, or you will see in upcoming weeks. And it's geared towards those of you who have a strong math background but are not at all familiar with results from learning theory. So if you're an expert in the area, certain days may be less exciting to you than others. Let me just mention briefly what I mean by supervised learning. So in a supervised learning scenario, a learner is given some data. So one common example is from computational biology, for example, is protein classification. So this is probably the only example that I'll give throughout the mini course. In protein classification, you're given a sequence, many sequences of amino acids. Some amino acid sequence. And you can imagine that some biologist runs an experiment in a lab and wants to know whether it belongs to protein family A or not, some particular protein family. So you get an amino acid sequence, and after some expensive experiment that you've run, you label it plus if it belongs to the protein family, and look at some other amino acid sequence, you run some other complicated experiment, you figure out that it doesn't belong to some protein family. And so you end up with this large labeled data set. And of course, running these experiments is expensive, so what you'd really like to do is uncover some sort of structure in this data and come up with some representation of the data H, which is frequently referred to as a hypothesis, so that when you receive, hopefully when you get a new amino acid sequence and you'd like to classify it, instead of having to run some expensive biological experiment, you can plug in the amino acid sequence into this hypothesis H, and it will fairly accurately tell you, yes, it belongs to protein family A, or no, it doesn't belong to protein family A. And the notion of supervised here corresponds to the fact that the data that you're given comes associated with a particular label. And typically, this label will be +1 or -1, true or false, so it'll be binary. On the other hand, what's nice about this primitive of classification, so supervised learning is often referred to as classification, is that if you'd like to do some other learning task, say that has more than one label, it typically reduces in some interesting way to to classification. So it's a very powerful primitive. For example, if you'd like to do optical character recognition, you can buy very expensive software packages to do OCR, and you have some text, and you'd like to know, is each character, you just like to recognize the characters of the text automatically, and you want to determine, you could run a classification task to determine if each character in your text is a 5 or not a 5. That would be one way to do multi-class classification using binary classification. There are other more sophisticated ways. There's a whole literature on it. So one example of a problem that is not a supervised learning problem would be, so something I will not be talking about, would be clustering or learning mixture models. You can imagine you're given some points in Rn, and you would like to find centers of the points that cluster them in some particular nice way. That's another way of finding structure in data, and I just won't be covering it during the mini course. It's a huge, interesting field. I don't mean to disparage it in any way. We just won't be looking at it. So. Let me just say that, OK, so let me start off with another example that will lead us into a variety of things that I want to talk about. Since I won't be talking about it. So one method you might use to come up with some succinct representation of, say, this database with amino acid sequences labeled according to whether or not belongs to some protein family, would be to use a decision tree. So if you're not familiar with the decision tree, I'll just define it using a picture. It's a tree. There's some root node. You're attempting to classify this particular data. So maybe at the root it says, look at index x5. Look at the 5th index. If it's an A, move to this node in the tree. If it's a G, to this node in the tree. Or we could say if it's an A or a T, if it's a G or a C, this way. And then this node might say, OK, well, now look at the index 10 in this amino acid sequence. This way. And so on and so forth until you get to the root that could be labeled +1 or -1. And so on and so forth. And we'll say the depth of this decision tree is the length of the longest path from root to leaf. And the size is the number of vertices.
Maybe
so one thing that
a little bigger.
Oh yeah. Do you want me to write? You want me to write bigger? Thank you.
Yeah. Well,
From
fine as is, but it's
okay.
Or maybe I'm getting old.
Will do. Thank you.
Or maybe you're sitting in the back.
Right. So one thing that's commonly done in data mining is you would take this this set of labeled examples, and you would run some algorithm, which I'll talk about in a second, and you would hope that you would find some relatively succinct decision tree that does a good job of classifying, say, in the best case scenario, all of them, but at least most of them correctly. And of course, what's trivial would be to come up with a decision tree that is the size of the set of labeled examples that you're given. Okay, that's totally trivial, and it makes sense that it's totally uninteresting. It has no expressive power. You're taking you could call this just some table of all of these labeled examples, and you're returning it back as your hypothesis. You haven't done any learning. You've merely copied over the labeled examples that you've received. So trivial would be, a decision tree of the same size as the data. But now what's interesting is we can consider the complexity of the following problem. It's problem 1. Given a set of labeled examples, the promise that there exists a decision tree of size S consistent with data. So I'll tell you that there is some decision tree of size S that's consistent with the data. What is the complexity finding such a decision tree? I'll say a consistent decision tree. Okay. So as I mentioned, machine learning practitioners frequently will take a data set and run some particular algorithm and come up with a decision tree that hopefully classifies much of the data well. But when we kind of more formally look at this problem, so I can define it this way, given a set of examples, I'll tell you that there's a decision tree that's consistent with this set of examples. What's the complexity of finding such a decision tree? It's open. In fact, the best known algorithm is originally due to Ehrenfeucht and Hausler. Also, there's a simpler proof due to Avram Blum. Runs in time, order n to the log s, where n is the length of your attribute of your data points here. It's the dimension of your data when thought of as vectors, and s here is the size of your consistent decision tree. Okay, so it's still open as to whether or not there's a polynomial time algorithm that will output, say, the best a decision tree that's consistent with your data. And also, what's interesting is that on the hardness side, I'm not aware of any. Well, I should be careful about this. There are some hard. Well, I'll get to it in future lectures. The hardness is a bit more complicated to describe, but there are some hardness results that of a restricted nature, but in general, hardness is still kind of unknown.
The cardinality of S doesn't come into. Just have to look at the data, right? Or sample from it.
Sorry, what's your question?
There are two parameters which unfortunately we call both of them as one
Yeah.
is biggest and one is smallest, but it's okay.
Okay.
No, yeah. So this S is the exponent there, log is the smallest, I presume.
Oh, yeah. Sorry.
Yeah, but
Okay.
I'm asking now about the role of the big S. I mean, of course you have to look at all the data.
Oh, right. Right. Yeah, good point. Yeah, right. I was a little sloppy here. Okay, there are a couple of ways I could get around this. I guess what I'm trying to say is that So really what you want to do is what you want to do is fix n and s and draw a sample of sample s of labeled examples. And I'll let the size of S be polynomial in n and s.
So there is then some probabilistic aspect? Or
Yeah, there's some, well, the way I'm trying to get around this is basically imagine that you've fixed n, the length of your example, and s, the decision tree. Then you're going to draw some sequence of examples. And then now I've kind of eliminated the randomness. It's just an algorithmic problem. You have this fixed sequence of examples. You'd like to know what's the complexity of finding a decision tree that fits. Okay.
I'm sorry, and of course
Yeah.
there are lots of very natural variations in this, right? You wouldn't mind if you come up with a tree that's slightly bigger than the optimal, and you wouldn't mind if there is anything probabilistic that you err on a very small fraction.
Yeah, exactly. So I'm going to get to all of these. I'm just trying to give a motivating example. And in particular, like, you could set the parameter little s to be, I mean, in that regard, you can kind of take s to be any polynomial you want to be in little s. Yeah. Good. So I'm going to talk about decision trees. So let me now that I've sort of mentioned let me make one sort of trivial observation, and that is that if p equals np, then this task is easy. Because I can simply guess a decision tree of size little s and check that it's consistent with all of my labeled examples. So this is really an interesting computational problem where we don't know the best known, the algorithm is, the best known algorithms are far from being polynomial. We don't have any satisfying hardness results. And it's also a problem that's used very frequently by practitioners. So the sort of hope is that, or the possibility that's out there, is that there is some algorithm that we've missed, and that's sort of one of the motivating reasons for continuing to study these types of problems. So let me just kind of pause here and give an outline for what I want to do for the rest of the mini course. So today, I'm going to talk more about decision trees. And I'm going to go over some of the real, seminal or classic results in computational learning theory from probably 20 years ago. So this will involve so it would be an algorithm, a query algorithm for learning decision trees. This is due to Kushilevitz and Mansour. And I'll mention the low degree algorithm of Lunio, Mansour, and Nissan, which sort of introduced the Fourier method into supervised learning. And hopefully I'll get to talk about Hunta's and Mansour's conjecture. So what I'd like to get through today are sort of the classic results from supervised learning from 25 years ago that are very related to kind of Fourier learning and some of the topics that Shistov will be discussing. Then on day 2, I'm going to talk about learning with noise. and also connections between, hopefully connections between noise stability and other topics from the analysis of Boolean functions to learning. Then once we've done, kind of talked about all of these algorithms, so I'm going to try and focus on algorithmic aspects of all of these results. Whenever I can, I'll sort of state the necessary kind of structural theorems, but I won't have time to really prove any of them. So after these kind of initial concepts on learning and then learning with noise, on day 3, we'll talk more about learning high-dimensional convex sets. So on day 3, I'll sort of be using some of the results from day 1 and day 2 to be able to talk about some connections between high-dimensional geometry and learning that will be very related to some of the things that we've talked about in days 1 and 2. But some very interesting results from analysis will come into play here on day 3. And then on day 4, I would like to get back to talking about hardness results, various reductions among learning problems, and also hopefully kernel methods. On day 2, in the learning with noise section, we'll probably also have to make a digression into boosting algorithms. So this is my plan. OK. So getting back to learning decision trees, it's a nice open problem. There's one, if we give the learner extra power to try and learn these decision trees, so if the learner is allowed query access, then we'll see that we can actually do much better than if we're just given a randomly sampled sequence of set of examples. So let me define what I mean by this. Let me give you a more formal setup. So I'm going to fix C to be a class of functions. And in particular, I'll let C be the class of size S decision trees. And so I'll treat every C in C. Well, for right now, we'll map 0, 1, n, minus 1, 1. OK, so typically, C here is a Boolean function. And the script C is often referred to as a concept class. And I'm going to assume that a learner is given black box access to the unknown C in C. Okay, so the learner pick x in 0, 1 to the n of his choosing and receives f of x. And the goal is to output some hypothesis H such that the probability from x and 0, 1 to the n that h of x does not equal c of x is at most epsilon. Okay, so I've already made, so this is the, I've already kind of changed the model that we're working in. When I mentioned this particular problem, there was no, this was sort of a distribution independent setting. You were given a labeled sequence of examples. You had no idea what distribution they came from. And you were asked to find a decision tree that was consistent with this set of labeled examples. Now I'm making the task, and this is a difficult task. So now I'm making the task much easier. I'm putting an underlying distribution on the space that we're working with. So I'm assuming that we're trying to learn with respect to the uniform distribution on 0, 1 to the n here. And I'm doing that by saying that your hypothesis that you output has to be correct, but it has to be correct only with respect to the uniform distribution on examples. And furthermore, I'm letting you pick the examples that you would like to see and their labels. So in the kind of classical decision tree learning problem, you're simply given a batch of labeled examples, and you're asked to find some decision tree that fits the sequence of examples. And this is sort of the uniform distribution learning problem. Now, of course, we'd love to learn decision trees with respect to arbitrary distributions. I would love to say, you know, you're given examples from some decision tree chosen according to some arbitrary distribution, and you're able to output some hypothesis that agrees with the unknown decision tree with respect to this arbitrary distribution. That would be great. But you know, we have to start somewhere, and it's a considerably easier problem to make an assumption on the distribution. So we'll see, you know, throughout the mini course that we'll have to make a variety of, you know, hopefully weaker and weaker assumptions on the distributions that we'd like to learn with respect to. So the kind of one of the most common restrictions to make is the uniform distribution on 0, 1 to the n. And also another thing to note here is that I'm allowing the learner to output a hypothesis, h, and I've said nothing about the structure of h. So h need not be a decision tree. H just needs to be some polynomial time computable hypothesis. So it doesn't have to be a decision tree. And we'll see that in the algorithm I'm about to describe that it's not. Questions about the learning model or anything? Okay. Yeah.
Don't you have to put some restrictions? I mean, otherwise a hypothesis could just be, I mean, you pick polynomially many samples, right?
Yes.
I mean, the hypothesis could just be output 0 if you haven't seen it, otherwise output what you have seen.
Right, but so, I mean, that hypothesis, when you receive a new example that you haven't seen before, what's it going to do? It's going to say 0, right?
Yeah.
That's going to be a bad hypothesis. I mean.
Okay, so you say kind of this is something, actually it's kind of legal to do, but it would be stupid, it wouldn't satisfy this at most epsilon condition.
Right, you want the hypothesis that you output to have some sort of generalization power.
Oh, but otherwise it can be just anything.
Otherwise it can be anything. So
Also somehow there is an and there, which we did not clarify the quantifiers, but I think if the quantifiers are clarified, are defined right, then your question.
yeah, so it should be that, what you want is an algorithm A, so a fixed algorithm A, such that for all C and C, when given access to this concept class, it outputs a hypothesis H that is epsilon accurate.
So you don't know what C is, right?
You don't know what C is.
So you want H to be epsilon far from all C's which are consistent on the samples, on the queries that you've made?
From the class script C.
You want a hypothesis that's epsilon close to, I mean, you don't have to necessarily output C, but you need to output
No,
some.
I'm saying that there might be more than one C which
Absolutely.
agree on all those queries that you made.
Absolutely, so you can output any one.
No, I mean you want to be epsilon far from all of them. Does that mean the same? Epsilon close to
Epsilon
all of them.
close.
Yeah, epsilon close to all of them.
Right.
Okay.
Right. So, I mean, let me just say, kind of as an aside, you know, there's this notion, there's this old notion in learning theory called basically Occams Razor, or compression implies learning. Which basically says that, well, this is really sort of an aside, but if you want to learn a concept class C, it suffices to take, let's assume that the size of C is finite. It suffices to take roughly log size of the concept class, the function class over epsilon, random examples, and output some C that is consistent with the examples. So this is sort of a sufficient condition for doing distribution-independent learning. You have some fixed concept class C. You can choose roughly order log size of the concept class over epsilon examples. And if you're able to find some function in the concept class C that is consistent with this sequence of labeled examples, then you'll have this guarantee that the consistent concept class, the consistent function that you've output, actually is epsilon accurate with respect to the entire distribution. So this is a sufficient condition for learning with respect to any distribution. You can take some batch of examples, you can find a function that's consistent with this batch of examples, and with high probability, this function that you've output will be epsilon accurate with respect to the entire distribution. So it will have the kind of generalization power that you were asking about. Now here, and kind of for the rest of the week, we'll be talking about a case where the distribution is not arbitrary, it's some specific distribution. And so we won't have to rely on using this type of condition to show that your hypothesis has some good generalization power. We'll be able to say, use the fact that we're working with specific distributions. So let me show you the algorithm.
Recovering a decision, it's kind of not the same problem in the sense that a small size decision tree converted into a polynomial will have a lot more structure, right? In the sense that, for example, here all the terms will have x1 or 1 minus x1 as a.
Yes, you're saying it's more than just an arbitrary sparse polynomial.
It's a lot more, right? We don't know of a sort of a polynomial reduction between the two.
So you're saying I don't know how to go from the polynomial back to the decision tree. Yes, absolutely. So that's why I was emphasizing the fact that the learner doesn't have to actually output a decision tree according to this criteria. It just has to output some polynomial time computable hypothesis. And what it will output will be a sparse polynomial. Okay. So it's going to be convenient. It's going to be convenient to shift from the 0, 1 to the n domain to the +1, -1 to the n domain. So I'm going to view all of these decision trees as mapping +1, -1 to the n, +1, -1. Okay, so it's a change of basis. And in which case, after this change of basis, this polynomial will become it will then be the Fourier polynomial for this decision tree. So let me just talk about this kind of for 1 second.
So note that when you are changing basis, since we're talking about sparse polynomials,
Yeah.
then the sparsity is going to change because.
Well, so let me get to that in a second. Yes, the sparsity will change, but the L1 norm will not change. So.
The polynomials we are constructing are in fact sparse in the Fourier basis, right? They're not sparse in the standard basis.
I mean, if you're, I mean, strictly speaking, you know, if you define sparsity to be the number of non-zero terms, then it's not going to be sparse in the Fourier basis. But it will be closely approximated by something that is sparse in the Fourier basis. Let me get to it in just a second. Okay. So, so since we're trying to learn, my perspective on you know, learning with respect to particular distributions is one from sort of an approximation. I'm running out of sort of an approximation theory perspective. Okay, so we have some function from +1, -1 to the n to the reals, and the distribution, the underlying distribution, is uniform on +1, -1 to the n. Now, anytime you have a set of functions that are bounded in some way, and here they're Boolean, so they're all bounded, and you have a distribution on some product space, you can look at an orthogonal family of polynomials. These are polynomials, these are a family of polynomials. In the univariate case, it would just be, well, let me just say these are, so there's some index set. Say I have some polynomial P, S indexed by S, and some polynomial T. In this particular, so basically what's going to happen here is you're going to come up with some family of polynomials and some inner product where for every two polynomials that are different, their inner product is going to be 0. For every two polynomials that are the same in this family, their inner product will be 1. And these polynomials are going to be dense in L2 with respect to the functions that you're looking at. Okay, so I guess for this particular, I mean, Shestov will probably talk much more about this, but for this particular case, the orthogonal family of polynomials that we're interested in will be parity functions. On the variables x1 through xn. And for S, some subset of n will define chi of S of x to be the product of the variables in S. Okay, so if chi of 1, 2 of x is just going to be the monomial x1 times x2. So my orthogonal family of polynomials here are going to be all 2 to the n monomials of length n. And the inner product, so if I have two polynomials, chi s and chi chi t, we'll have that the expectation of chi s times chi t, this is going to be the inner product, where x is from minus 1, 1 to the n, will be 0 if s does not equal t, and 1 if s equals t. The reason why I'm mentioning orthogonal families of polynomials here is that in later lectures, instead of learning functions that map from +1, -1 to the n to r and the uniform distribution, we'll look at functions f that map, say, Rn to r, and the distribution might be Gaussian. For example, so instead of being uniform on the cube, the distribution might be Gaussian. And then we'll have a different family of orthogonal polynomials. They will still have the nice property that, with respect to a particular inner product, any two different, it'll be an orthonormal basis for the family of functions that we're interested in. So for any two functions that are different, their inner product will be 0, and for any two basis functions that are the same, the inner product will be 1. And as I mentioned, these polynomials are dense. This orthogonal family of polynomials is dense. So what does that mean? Well, in this case, it means that for any f mapping +1, -1 to the n, r, f can actually be written as some linear combination of these monomials. So I'm using this notation, but I like to think of it as just, for any function mapping the hypercube to the reals, because you have this nice orthogonal family of polynomials that's dense with respect to this function class, you can write f as some linear combination of these monomials. And in order to describe this particular algorithm, the only other fact I'll need is Parsifal's equality, which says that the expectation of the square of the function is the square of the Fourier coefficients. OK, so to see if this made any sense, let me state the following fact that should be easy. So if f is Boolean, and g not Boolean, but we have that the expectation of f minus g squared is less than or equal to epsilon, that it implies that the probability that the sine of g is not equal to f of x is at most epsilon. So what this basically says is that I have this decision tree. I'm going to think of it as some unknown polynomial. And I've shifted from working from 0, 1 to the n to +1, -1 to the n. So I'm thinking of it as some linear combination of parity functions. And remember, you have black box access to this unknown polynomial. And if you can find some function g such that the expectation of f minus g squared is at most epsilon, then your hypothesis that you're looking for, what you want to output, is the sign of g. Okay. Because the sign of g will differ from f in at most epsilon. So this is going to be the hypothesis that you're interested in outputting. So this is an easy fact. So let me recast what the goal of this algorithm is. It's so you're given black box access to F or to C. And you would like to minimize over all polynomials P sparsity at most T the expectation of C minus P squared. And this is what you want to approximately minimize. So we've taken the task, which is learning an unknown decision tree, and you're given black box access to this decision tree. We've reduced it to the task of minimizing over all polynomials that have some sparsity parameter t, the expectation of C minus P squared. Okay, so I guess at a high level, you have black box access to C. It's some unknown polynomial. What is the polynomial that of sparsity at most t that minimizes this quantity? Well, the answer is that it's the polynomial that takes the t largest coefficients of p. So the minimizer, this quantity is the polynomial p that takes t largest coefficients. And this is easy to see because by Parsifal's equation, this expectation is exactly the sum of the squares of the coefficients of p that you did not take. So note that if I had written here instead of expectation of C minus P squared, if I had written expectation of absolute value of C minus P, then it's suddenly less clear what polynomial you should take. But because we have the 2 here, because we're working with respect to the 2 norm, and we have Parsifal's equation, it's clear that the polynomial that minimizes this program is the one that just takes the largest coefficients of your unknown decision tree. Okay.
So do you mean that it takes the t largest coefficients of C?
Yes. Did I say P? Sorry.
Absolute value.
Sorry?
Largest in absolute value.
Largest in absolute value. Yes.
Yeah, then it should be C. The last, you have 2
Oh,
keys there.
sorry.
The second one should be C.
Sorry. And that's what this particular algorithm is going to do. And the way that it's going to do it is so the algorithm is actually, it's very beautiful, it's very simple. So again, you're going to build a tree. So here I'm going to have C. And on the left half of the tree, I'm going to come up with some function, which I'll call C1. Let me just, yeah, some function which I'll call C1. And this is going to correspond to the sum of the squares. So I guess sum of, how should I write this? Such that S begins with 0. So literally, I'm going to fix, every monomial can be indexed according to a string, and I'm going to fix the first bit of this string to be 0. So think of this is sort of we're building a prefix to this coefficient for the name of this coefficient. And on this side of the tree, I'm going to have the sum of all the squares of the Fourier coefficients, where S begins with 1. So the sum of the squares of all the Fourier coefficients, the sum of the squares of all the coefficients of C is equal to the sum of the squares of all the coefficients on this left branch plus the sum of the squares of all the coefficients on this right branch. And then I'm going to kind of, so remember, so the goal here is to find large coefficients of C. So I know that the sum of the squares of all the coefficients is 1. It's a Boolean function. So here I'll get some estimate on the sum of the squares of all the Fourier coefficients that begin with 0, and here with 1. And then here I'll get an estimate. We'll estimate what the sum of the squares of all the Fourier coefficients where the coefficient kind of begins with 0, 0, and where the coefficient begins with 0, 1, 1, 0, and 1, 1. And we'll recurse, and at the bottom of this tree, we'll have a string of length n. And this will correspond to exactly one Fourier coefficient. It'll correspond to the coefficient that has this as its index. And so it's sort of a recursive procedure. The algorithm will look at the sum of the squares of the Fourier coefficients going this way and on this branch. If at any time it finds that the sum of the squares of the Fourier coefficients on one particular branch is very small, it will abandon its search on that branch, and it will continue its search down some other particular branch. Okay, so let me just. To this end, let me define a function C alpha of x, just so I don't get this. So this is going to be the sum over all z. So alpha is going to be a string of length k, and then we'll sum for z in 0, 1 to the n minus k, c hat of alpha z. So this is a function. And you can see that it sort of corresponds to all of the Fourier coefficients where that have alpha as a prefix of this particular Fourier coefficient. So, for example,
the subindex should be that alpha z as well.
Alpha z is of length n.
Right, but for the chi, the chi, should the index be also the subindex? You wrote chi sub c.
Yes.
Alpha z.
No, I don't think so.
So either there should be alpha z or there should be a constant term corresponding to the branch. A constant plus minus 1 by the
The question is, are those taken over a lower dimensional cube or are they
Yeah,
lower
they're taking over a lower dimensional cube.
Then you're free.
Yeah.
No.
I mean, x here is in 0, 1 to the n minus.
No, but then, so if you want to express C as C0 plus C1,
No, I don't. I mean, I guess I want to say that.
Minus 1 to the other product.
right.
So it's up.
Well, C of the empty set of x should just be C of x. And then expectation of C squared should equal expectation of C of 1 squared plus expectation of C of 0 squared. And the main theorem is that C alpha of x is equal to the expectation of y Cy of x chi alpha y. Furthermore, C alpha of x. So why are we in good shape if this theorem is true? Well, it gives us a way to actually, with query access, remember we have query access C, and we'd like to be able to sample the x, so we want to be able to sample, we want to estimate expectation of C alpha x squared. Because this exactly corresponds to the sum of the squares of the coefficients that have alpha as a prefix. So if we have this theorem, we're in really good shape because I want to estimate the expectation of C alpha of x squared. So what will I do? Well, I'll sample random x's. For each x that I choose, I'll sample random y's to estimate this particular expectation. And then you can see if you want to estimate C alpha of x to any additive epsilon, it's simple. I can pick random x's. For each x, I can pick random y's. I'll get I'll get within some additive epsilon a very good estimate of C alpha of x. And so that will give me a good estimate of the expectation of C alpha of x squared. And that will be sort of the sampling routine that I'll need to carry out this recursion.
This just works for uniform when you receive uniform values.
Yes, this is all for the uniform distribution, right? Can you say your question again? I mean, I'm allowed to query on any point that I want, so.
Sometimes it's concatenation.
Sorry?
This is concatenation.
Yeah, this is concatenation, so.
Oh, yeah.
It's important to have query access, right? It doesn't work if you're giving random examples.
Yes, well, as I said, yeah, so that's an unknown hard problem, right, that I'll be talking about in a second. So, so just so we can say we did one proof. I'm going to consider this quantity. And I'm going to expand out cy of x. And then I'm taking my expectation over y. So everything that doesn't involve y can be pulled out. And then I'm left with the expectation of y of OK, so here I have two monomials, chi of z1 and chi of alpha. And my expectation is over.
You want y. There is a z1 where it should be y.
Oh, yeah, sorry. Thanks. So here I have an expectation over y here of two monomials. So this is going to be 0 if z1 does not equal alpha and 1 otherwise. So what I'm left with when you make this simplification where z1 has to equal alpha is just the sum over z2, c hat alpha z2, chi z2 of x. This is, I guess, did I have y here? No, x. And this is exactly what we wanted. This is the theorem. This is exactly the definition of my function where the prefix is equal to alpha. Okay. So given this theorem, as I said, we know how to sample now, or estimate the sum of the squares of all coefficients of the polynomial that begin with some particular prefix. Now, the depth of this recursion, so if you consider this like a recursive algorithm, the depth of this recursion is at most n. And the width of the recursion so I guess I should have had an input parameter, theta, and you want to return coefficients that are greater than or equal to theta. The width of this recursion is at most 1 over theta squared. Well, there can be at most 1 over theta squared coefficients that have magnitude greater than or equal to theta because the sum of the squares of all the coefficients is at most 1. So you have this recursive algorithm. The depth is at most n. The width is at most 1 over theta squared, where theta is the input parameter of the size of the coefficient that you're looking for. And so this implies that the algorithm is polynomial in n, 1 over theta. And then, of course, epsilon here is going to correspond to some error that comes into play when you do all of this sampling to try and estimate the sum of the squares of the Fourier coefficients. But still,
what's the algorithm? Did you expand the leaf with the highest value?
You expand the branch. So for any branch where the sum of the squares is less than theta squared,
We continue.
you end.
Otherwise, we're both.
Okay, fine.
Yeah. You terminate. at a very high level, you're kind of fixing prefixes. You're kind of restricting the label of the coefficients of the polynomial until you can kind of hone in on ones that have large magnitude. And as Johan said, you absolutely need query access in order to estimate the sum of the squares of the Fourier coefficients on any kind of branch of this tree. Good. So if you want to minimize, as I said, if you want to minimize the expectation of c minus p squared over all p, where p is t sparse,
Sorry, there's no third epsilon, right? What's the epsilon?
this is well, you want to approximately minimize this quantity. So you're going to output a p such that expectation of c minus p squared is less than or equal to epsilon. So there's going to be some error, and this epsilon will play into the error of that particular epsilon. But as I said, once you've found this p that is essentially all the large coefficients of the polynomial that corresponded to that decision tree, then you can just output the sign of p. OK? So questions on that? So I'm not done, but so tomorrow I will discuss what happens when instead of minimizing expectation of c minus p, you want to estimate absolute value of c minus p. And there are good reasons for doing this. And the algorithmic problem becomes much harder because it's no longer, as I said, it's no longer clear that the best thing that you should do is to just take all of the large coefficients of c. But we'll talk about that tomorrow. OK, great. So what's still open is, well, there are many open problems, but one is if the learner does not have query access, C, and instead receives uniform random examples, can you still learn the underlying decision tree? Or can you find all of these large coefficients of the underlying polynomial? This is open. And I definitely don't know of any good hardness results for this particular problem. So there are two kind of related questions. One is,
when you say something is open, do you mean you don't know how to do it in polynomial time, or you don't know how to do it better than brute force?
Good question. We definitely, which I was going to talk about in just a second, we definitely know how to learn decision trees in quasi-polynomial time. So just the polynomial time algorithm is what's unknown. There are two related questions that I wanted to talk about. One is learning groups. The other is learning TNF formulas. So we'll see in a second. This is an easier problem. And this is a harder problem. So let me talk about the harder problem for just a second. Recall that when you have a decision tree, it's easy to see that any size S decision tree can be computed by a DNF formula with S terms. For example, if I have a decision tree here, this is x3, x7, x4, and let's say that this goes to +1, then I can consider the term x3 bar and x7 and x4. This is a term, you can just take the OR of all of the terms that correspond to paths that arrive at a +1 in a decision tree. And since they're at most, it's of size S, they're at most S leaves, you'll get a DNF formula with S terms. And a natural question is, given a DNF formula with S terms, does there exist a polynomial P such that, well, does there exist a sparse polynomial P that approximates this DNF formula? So let me write it this way. Does there exist a polynomial P such that P is S to the order log 1 over epsilon sparse, and expectation of DNF formula F, expectation of P minus F squared is less than or equal to epsilon. So it shouldn't depend on n. The question is, given a DNF formula, you have S terms. Is there a polynomial P with sparsity S to the log 1 over epsilon that epsilon approximates this particular function? If so, then by using the algorithm for learning decision trees for finding large Fourier coefficients, then there is an S to the order log 1 over epsilon time algorithm for learning DNF formulas. Okay, and this is Mansour's conjecture. And actually, it would be interesting. It's open, and it would be interesting to prove an S to the f of epsilon bound, where f is any function of epsilon. This is still not known. So this conjecture was made, I think in like 1993. I could be wrong about that. And the motivation was that since we know how to learn decision trees when the learner is given query access to the decision tree, if we could prove just this structural result about DNF formulas, then we would immediately get a learning algorithm for DNF formulas. Now, it just so happens to turn out that, that Jeff Jackson gave a polytime algorithm, a polytime query algorithm for, I'll say, polynomial size DNF formulas that did not resolve man-source conjecture. So you may be wondering, well, sort of who cares about man-source conjecture? We know that you can learn DNF formulas given query access. It's a really great result. But we'll see tomorrow when I talk more about learning with noise that this conjecture still implies some interesting things that we don't know. And so we know some very kind of we know that man-source conjecture is true for some very restricted settings. For example, if the DNF formula is randomly chosen appropriately from some class, then we know that this conjecture is true. But otherwise, nothing is known. And so the other question that I wanted to talk about is learning hentas. So a k junta is a function f. It's a Boolean function that depends only on k input bits. Now, one thing to notice So the interesting open problem and what's unknown is, so it's easy to see actually that if your learner is given query access to this unknown function, then you can learn it. You can find, the difficulty in this particular problem is finding what these kind of relevant k input bits are. And if the learner is given query access, it's easy to see that you can sort of solve this problem. The open problem is just given random examples, from +1 - 1 to the n. So you're not allowed, the learner is not allowed query access, but you're still given uniformly random examples from +1 - 1 to the n. You want to output, it's the usual criterion, you want to output an h. So f is an unknown k junta. You'd like to output an h such that the probability x epsilon. One way to solve this particular problem is to use brute force search and to enumerate all sets of k relevant k variables, and basically see, once you've picked your set of potentially relevant variables, you can see if in fact, you could use brute force search and search over all possible functions on those k input bits and see if you've found the right set of k relevant variables. It's not difficult to see that this works, and it'll have a running time of n to the order k times some function of k. This will correspond to, say, doing brute force search over all possible functions on k variables. But it's this term that you're trying to improve upon, and what you'd really like to do is have a running time of, say, n to the little o of k, or for example, 2 to the k times poly n. This would be very interesting. So one thing to note, so note that any order log n junta is computed by a poly-size decision tree. Okay, so this is to say that, and certainly, we definitely don't know how to learn log n juntas in polynomial time. So this is to say that the decision tree problem, namely learning an unknown decision tree when you don't have query access, is harder than the junta problem. I mean, if you, it's a good motivation for studying the junta problem. If you're really interested in learning polynomial-sized decision trees, then you really need to make progress on the problem of learning k-juntas first. Okay, and
can you do better than n to the k? I mean, can you even get this n to the k over 2 or something?
Yeah, so I was going to say that I was going to sketch so Elkanon, O'Donnell, and Servideo gave an n to the, I shouldn't say O, an n to the omega over omega plus 1 times k time algorithm, where omega is the matrix multiplication exponent. And there's been a recent work by Greg Valiant that improves this slightly. I can't remember exactly what the, it might be, he might be able to do n to the 0.68k. I forget. It's actually a very cute result that if I have time I'll get into. But maybe, since I'm out of time, basically what I'll do is I'll finish up a couple of loose ends from this lecture, including this result. And then we'll start talking about learning with noise and discuss some more sophisticated optimization problems corresponding to minimizing with respect to L1 norms instead of L2 norms. Okay. So I'll stop here.